And go! Continuing with graphs and models and finding points of intersection. So you've done a ton of this before. Mainly you did it with finding the points of intersection between two lines, but we're going to ramp things up a little bit. Before we actually solve this problem that I have for you, blah, 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 blah. Let's talk about this first because I have a little quandary. Let's start with the right equation. What can you tell me about the equation on the right? It's linear. Good. How about, what's the slope of that line, by the way? 1. Good. Okay, how about the equation on the left? What can you tell me about it? What's it awkward? Can't tell me anything about it? Now it's getting really awkward.
It's a parabola.
It's a good start. Does that parabola open up or down? Why?
Because you can subtract the x squared and divide by the negative on the y.
Good. Good. And the reason I ask why is because a lot of people just look at that and say, well, there's no minus sign in front of the x squared, but realizing it's on sometimes the y, you got to do all that business. So we have a parabola that faces up, and we want to intersect it with a line. So the question is, how many different ways, not this particular quadratic, just any quadratic, how many different ways can a line and a parabola intersect? So just draw little sketches in your notes of the all the different ways that they can intersect, and how many points of intersection can you get?
2, 1, or 0.
Did you break your water bottle?
No.
Man?
Mm-hmm.
Oh, it just looks broken. Take a picture for that?
Right, draw the ways to intersect. Yeah.
So what are you worried about?
Nothing.
Okay. Golf clap. Any other possibilities? No intersections, one intersection, two intersections. No other possibilities. No other variations of any of those. Well, yeah, we could take the no intersection and move it over on the right-hand side. We could move the 0 intersections down below. We could flip the 2 intersections over and make it have a negative slope. What about the 1?
Yeah, Ashton.
Mm-hmm.
1 point of intersection. Good. You know what that's called, by the way?
Tangent.
It is called a tangent. You're going to spend an incredible amount of time in this class working with tangent lines. Touches in only 1 point of intersection. No other possibilities. Now, suppose instead of this being a quadratic, I change this to a cubic. Now, how many ways can they intersect? Draw some pictures. I guess I should have asked the question, is it safe to assume you all know what a cubic looks like?
Yeah.
Okay, good. So for the quadratic, we had three possibilities. No intersection, one intersection, two intersections. How about for the cubic? What are our possibilities, Tom?
There's also 3. Is there
You get 3 out of that?
3 possibilities?
3 possibilities, what are they?
1, 2, and 3. Yeah.
1, 2, and 3?
Oh yeah. that's-
No 0? Ooh, show me. That's 1. That's 2. Yeah, that's tangent, we got it. That's 3. And you can't do 0?
No.
What if you just go over to the right side over there and just draw a line even further over to the right side?
It'd still hit because it goes that way for infinity.
What if you angle it so it doesn't ever hit?
Oh, it'll hit down here.
Oh. See, right? So, I just want to make sure I understand this before we move on. We can't draw a line on that graph that won't hit the cubic. Okay. Does everybody see that? My argument would be, well, what about this guy? It's still going to meet? Where? Way down. Because again, that cubic is continuing to get bigger and bigger, not only up and down, but also left and right. Golf, Dr. Tom, please. Well done. Okay, now, find the points of intersection. Of the original problem, sorry, let me clean this up. Of this problem, let's keep it simple. Now hold on, I know you just dove into the problem, but here's another twist. Not only do I want you to find the points of intersection, I also want you to figure out at least 2 ways to accomplish that task. Last period we had 4 different ways to do this. I'm looking for 2. Did you talk about it or just dive into it? Oh, okay. I thought maybe you just dove in and you're all using the same method. And try to stay to the left. You get it? Yeah, for that problem.
Oh, those are just.
Well, that's not this problem.
I like the
That is a real one. On the right half of the board, she's going to be on the left half. When you're done, there's no rush.
Is it wrong?
No, it's great. Why? I'll get it from mine.
You have to substitute one variable for
I remember you. Just got to pair up your points. You got 2 points. -1, -2. Gold up, no.
Okay, how are you writing your list? Is there an eraser?
Then I think you just.
Is there an eraser?
Say again?
Is there an eraser? Because I didn't lift it. I didn't lift it up.
Make sure she's not writing, and then you just put your hand on it.
Oh, okay, perfect. Thank you.
You might be on.
Yeah, wait, yeah, let me erase this really quick. I can't write it well. X equal to 1 plus.
Oh, it's actually
While she's finishing up, get out your calculators and solve the same problem using your calculator. Just to make sure we're all on the same page and you all know how to use the technology. Do not use the trace function. Use the intersection function. If you don't know what that means, I'll explain in a second as soon as page is done.
Sorry, I lost my spot.
I understand. So now just that point is -1, -2. That gives you the first point.
I like lost my spot on my paper. That's why I'm like, because I didn't plug in.
That's fine.
Oh, I'm really struggling with this. Because I didn't plug in the second one on the board, so my work isn't shown there.
I was looking more for the technique than the actual approach to it. Okay, so give me your attention for a second. Put your calculators down. Let's talk about the two different methods. They both get the same results, which is fine. However, on the left-hand side, solve for x, continue through the problem, figure out what x is, plug it back in, figure out what y is, put it together in the 2 points. On the right, solving for y now, getting the y values, and then plugging them in to find the x values and getting the points. And notice the answers are the same, or you could erase. The answers, there we go. The answers are the same. That's 2. Number 3, obviously, is the calculator because I asked you to do that. Now, the AP people will expect your answers to be accurate to 3 decimal places when you're using a calculator. That's why I said don't use the trace function. Now, we have a problem where you get two nice, pretty answers. The trace function would probably work in this problem. But later on, you're going to be solving problems where the answer is 1.639, and you need to have it accurate to 1.639, and the trace function won't do that. Does anybody not know how to use the intersection function on the calculator? Speak now or forever hold your peace. You don't have to forever hold your peace, but I can help you with it later. Okay, beautiful. It's the 4th method. And by the way, up until last period, I would have said there's 3 methods, but somebody did something last period that I was like, oh, yeah, I guess that works too. So we're good. All of you either solve for x or solve for y. Is that an accurate statement? Okay. So this is what they did 4th period. They said, that's an accurate statement, right? Multiply the equation by -1. Why would they do that? Solving a system of equations. And you don't normally do this, but it does work. X squared plus -x is x squared minus x. The y's cancel. 3 plus -1 is 2. That should look familiar because we just saw it in the previous problem. You go through and solve it, and you're done. 4 different methods to solve the same problem. All of them are viable. All of them work. sometimes you won't have the calculator in order to do that. So you need to be able to solve it. If the functions change, things get quite a bit more complicated. So suppose we intersected that cubic with the line. Things get ugly. Suppose we intersect a cubic with a quadratic. Things get even uglier. Or we run a line through a circle. That kind of stuff starts to happen. Okay. Problems here? Beautiful. Okay. Did that. Mother functions. What are the mother functions? Say again? Not necessarily. Well, yes, for parabola, that's one. I'll start you with the most basic. Linear function. You spent an entire year in algebra probably dealing with just linear equations. How to find the slope, how to graph them, all that other fun stuff. The mother functions are the basic functions that we build everything else from. Whether it's graphing, whether it's solving systems. Y equals x squared is a quadratic, cubic. That's about where we stop. We will do a little bit of work with quartics, a little bit of work with quintics, but nothing very elaborate. Is it safe to assume you know what all those look like, yes? Yeah. Do you know what a quartic looks like? Looks like a W. And then a quintic looks just like a cubic. It's just either skinnier or fatter, depending on that. How about absolute value? What's that look like?
Looks like a V.
Looks like a V. However, do you know why it looks like a V? And this is kind of important as to what we're going to do in the future. So here's the graph of an absolute value. That's y equals the absolute value of x. The following question says, well, why does the graph of y equals the absolute value of x look like a V?
Because one of the values are always positive. The y is always positive.
Isn't that it? Is that it?
No matter what.
No matter what, we can't have negative y values, correct? We all agree on that, right? I'm going to show you a different approach that I don't know if anybody showed you before. If I start with just the line y equals x, do you all know what that looks like? Okay, good. Looks like this. Okay. So it's a line passing through the origin with a slope of 1. If I slap an absolute value around it, what that does is it takes anything below the below the x-axis and flips it up. And that's why it becomes a V. Why is that important? Well, the reason that's important is because we're going to start looking at more complicated functions that have absolute values in them that aren't V's. So, for instance, that. Any idea what that looks like? All right, bust out your calculators, graph that. After you get a graph, the question you want to ask yourself is, self, how did that graph come about? Easiest way to get to absolute value is to go to the catalog, which is catalog is above the 0. So second 0, absolute value is the first thing, in my humble opinion. You can also go under math, but I do the catalog.
Mine actually.
Su máquina de matemática. Your machine of mathematics.
Oh, I didn't put that. Yeah.
Are you surprised by the results?
Yes.
Because you expected a V, yes?
No, just the other.
No, you didn't. You just didn't expect it to look like that. Or were you on top of that? Now, here's the big question. Where did that picture come from? Thanks.
From the calculator.
Cindy? Beautiful. Okay, so let's do this. What does that look like?
It has a y-intercept of -3, and it opens up.
What is it?
Oh, a parabola.
Good. So this is what's called transformational graphing. You start with the mother function of x squared, and you know what the -3 does to it. The -3, like he said, shifts it down 3. So this graph, without the absolute value, would look something like this. Then, in a lovely shade of white, now the absolute value kicks in. And as Cindy said, the absolute value is going to take everything below the y-axis and flip it up. So then this stays the same. That's not hurting anybody. This stays the same because it's already above the x-axis. And then this puppy gets flipped up to here. Where's that? 3, good. Okay. Has nothing to do with a V. And that pops up a lot in the stuff we're going to be looking at. If you can graph the function inside the absolute values, then you can graph the absolute value by taking everything below and flipping it up. As soon as you see the absolute value, people make the mistake of saying, well, that's got to be a V. Now, what do I do with that V? You know, slide it 3, do all kinds of other things. No. If it's just a linear function, then yes, you'll get a V. But if it's not a linear function, you could get something funky like this. Okay. Semicircles? Well, I guess I should have included this. How about circles? What's the equation of the mother function equation of a circle? Good. X squared plus y squared equals r squared. X squared plus y squared equals r squared. You know what? Let's do this. All right. So what's the radius? 2. Good, not 4. Thought I could trick you. That's the entire circle centered about the origin with a radius of 2. What if I want a semicircle? I solve for the two variables. I either solve for x or I solve for y. So for instance, if I solve for y, I get y squared is equal to 4 minus x squared. So y is equal to plus or minus the square root of 4 minus x squared. Which one do you want to talk about first, the plus or the minus? Plus. Okay. 2 possibilities. Plus or minus, we're going to talk about the plus first. Is that the top or the bottom? You got a 50-50 chance.
Top.
It's the top. Negative is the bottom. So the 4 possibilities are you solving for y in a positive sense, top semicircle? Are you solving for y in a negative sense, it's the bottom semicircle? Are you solving for x? The positive is the right, the negative is the left. We won't solve for x very often because they're not functions. So we don't necessarily care about that puppy. Okay. Oops. Exponential graphs? What do those look like? Show me with your hands. Correct. Now, the spread of disease. The spread of zombies.
Oh, I brought Clorox wipes.
I understand how you got there from disease. That's why we have Clorox wipes, to help prevent the spread of disease and generate an exponential function. Zombie outbreak. Square roots. Show me with your hands. This will look good on the video, by the way. Yeah, goes well for this way. Yeah. It's the top half of the sideways parabola. We don't want the sideways parabola because that's not a function. If we just take the top half, we've got the square roots. There are probably others you've talked about. Did you ever do logarithmic graphs? Okay, what's that look like? exponential this way, logarithmic that way, right? The other one I didn't put up there, which I should have, is all the trig graphs. Sine, cosine, tangent, cotangent, secant, cosecant. Okay, we'll get to that later. All right, we're all done.